In the last class, we talked about the effects of sampling on computing statistics about networks. In this particular video, we're going to talk about how you might rectify some of that by being able to predict edges that you may have missed. And so again, just to remind you, when we're dealing with real complex networks, pretty much all of the time we'll be dealing with sampled versions of the real system. And so if you have some graph that is the true network, by sampling it by all the different ways that we collect graphs, we're inherently coming up with a sampled version of that where the vertex set and the edge set may be different. And so the question here is that we know that we've missed some edges. How do we identify edges that we may have missed, and so that we can add them back in? We'll see that many of these methods use generalized versions of similarity, and when you think about these methods, you can reflect back on our discussions about network alignment, which is a very related, under the hood, it's a very related concept in the sense that we're identifying nodes that are extremely similar. In this case, we want to add edges between them. Before, we were identifying similar nodes so that we could create a mapping from one to the other, from one graph to the other. When we talk about finding and recovering edges, one method, there are many, one method that you can use is some sort of classifier that's based on a whole bunch of different attributes about the nodes and the relationship between the nodes in the network. So we're going to denote this variable z, and it's going to be dependent on the two nodes that we'll be comparing. So in this case, we're dealing with say an undirected graph where u and v, we're looking at this edge, whether or not there would be an edge between u and v. And so in this case, we could have this vector could be composed of various different statistics about u and v and how they're similar. They could be network statistics, such as whether they have any common neighbors, or it could be other network statistics, similar centrality values, for example. And then you can also use elements that are statistics about anything that these nodes have in common, or anything to bring out their similarity. Could be occupation, if this is a social network. It could be hair color. It could be anything that is not a network statistic that would help to identify similarity. And so one classifier, this is not by no means the only one to choose, but one of the more direct methods is a logistic regression classifier. And in this case, the probability that u and v have an edge is going to be given by the logistic function, and that's this here. And so you've probably seen this sometime in your mathematical career. The sigmoid function is an example of the logistic function. And so I've got this figure from Wikipedia that shows this logistic curve, and it has this familiar S-shaped. And so by changing the values of the parameters in that exponent, you can make this S-shape be more steep, like this. And then you can also choose to shift this left and right. And so you'll notice that there's this constant term, B0 here, and that's actually the reason why we have this 1 right here in the first element, just because we'd like to have a parameter that would control essentially the shift. And so the example that that Wikipedia is using in this figure is they have a whole bunch of data points based on whether or not people pass an exam from various amounts of studying. And so logistic regression is one classifier that will classify essentially between a binary category. Here it's pass or not pass. In our network condition, it's edge or no edge. And so you can imagine this is essentially saying edge, that an edge should exist, and down here this is saying that there should not be an edge. And so just to kind of really make this concrete, think about this particular example of probability of passing an exam versus the number of hours studied. So clearly, if you don't study at all, you're more likely to not pass. And so these data points down here kind of indicate that. If you study a lot, you're much more likely to pass. But you can see that there's an amount of ambiguity here, essentially between these two spots. You get values of amount of studying here on the x-axis that lead to passing and not passing. And so this is an example of either noise in the system, noise in the measurement, or it could be the fact that there needs to be additional parameters. So how familiar people are with the material going into it, how good their background is on the topic, and so on. And so somebody here may have taken a very similar course and doesn't need to study as hard, whereas someone here maybe has not seen this material before, perhaps didn't have the prerequisites, and so didn't perform well despite more studying. So again, we use the logistic regression or any kind of regression techniques when there is inherent noise in the data, and that could either be because there's inherent noise, or that could be because there are alternative explanations that require additional parameters. And so the idea to transport this now into the network context, the idea here is that we will predict the probability. So this is the probability, this curve here is the probability that someone would pass. So clearly at 3 hours of studying, there's some ambiguity. In this case, this is maybe around 60% chance of passing. And so there it would be hard to tell for sure whether you'd pass or not. And so similarly, the role of the logistic regression is to use this sigmoid function to assign a probability based on, in this case, this high dimensional feature vector. What this is going to output is going to be a probability, and clearly at some point in time we're going to have to apply a threshold to determine, yes, I'm going to add an edge if I've got 90% probability or more. And so knowing when to add that edge is a little bit tricky and requires some base level knowledge about the rest of the edges. So the feature here is that this beta value is going to be something that maybe walking into this problem we don't know. But we do have a network that has a sampled network in particular that has a bunch of edges. And so we can use those edges in order to quote unquote train or learn this parameter vector beta. And so there's a beta element for each one of these elements of the similarity vector. And so it's going to give the relative weighting of each of these terms. And so really, the reason why this is called a regression is when we say learned or trained, all we really mean is that we're going to run a regression based on the data points that we have. Essentially, we can say, here's an edge, here's an edge, here's an edge, and we can train this beta based on those known edges. So this is a way to recover edges. And so what we're looking at now is the case where we may not necessarily be missing edges, but we could have more. So link inference is this idea that perhaps we don't have a ground truth network that we're trying to recover, but that there could be some element of adding edges or suggesting edges or recommending edges that makes sense in this context. And so you could imagine that if there is a network that represents movie similarity or perhaps music artist similarity, you could imagine that Spotify or some other music service would use that in order to recommend a new artist to you based on other people's, essentially based on this graph, which is composed of everyone's listening patterns. So if your particular pattern is missing some edges, then you may be able to be recommended to have some more. And so this again could use a variety of different ways of constructing this, but one of the most simple is the similarity measure. So if we use the similarity measures that we already have defined previously, this would tell us some information about whether or not I and J, nodes I and J, really ought to be connected. And so this is a real value, this similarity is a real value, and we're going to say that it's going to be not 0 if we want to infer the edge. But again, there needs to be some sort of threshold that says that this is big enough to be beyond the noise of the similarity measure. So we need something that's going to actually tell us that this is statistically different from 0, not just not 0. And to do this properly, you'd really need to have a couple of different features. And so we won't go in full depth, but you can kind of refer to statistics literature to know that you really need to have a crisp test statistic that you're going to use in order to determine whether it's statistically different across nodes. And then you also need to have this null model, which you have to assume what distribution this test statistic would come from. And finally, one thing that is not unique to networks, but one thing that comes up often in networks because of the fact that we would need to do this not just between nodes I and J, but all choices of I and J. And so the multiple hypothesis testing problem is that, and you can look at this fun comic, is that if we have a 5% statistically significant level, that alpha is 0.05, then that means that there's naturally occurring things that happen at a 5% rate. And so if we have to do 100 edge tests, essentially, if we're going to use this method to generate tests on edges, and we're going to do that over 100 edges, we would automatically assume that we would get 5 of them if it follows the null model that we're assuming, say normal distribution. There's automatically going to be 5 that satisfy this. So the multiple hypothesis testing problem is the fact that all of this construct of doing statistical significance and using that to test for significance based on a null model is really meant to be a one-shot test. And so if you're going to keep pulling from the same distribution sample after sample, you're automatically going to get something that falls beyond that statistically significant threshold, which turns out to be maybe not so significant. So there are definitely some challenges here. We've seen 2 subtly different definitions of this, one where there is a ground truth and one where there is not. But in both cases, we're establishing a similarity measure and then recommending or recovering edges based on that.